Assalamu alaikum wa rahmatullah. This is Professor Ahmed Alsaad. I would like to discuss with you in this chapter three concepts that will be very important for you in order to understand the axon and the nerve conduction that will be discussed later. In this part, I will go ahead and discuss the electric fields and electric energy. We will discuss also electric potential energy and electric potential, and then I will discuss the capacitance and the energy stored in a capacitor. Of course, as you know, electric field could be uniform and could be non-uniform. What is required in this syllabus is only the uniform electric field. And if you want to distinguish between uniform and non-uniform electric field, as you know, uniform electric field is the one that is constant in magnitude and direction, while the non-uniform electric field is the one that is changeable or varying in magnitude and direction from a point to a point inside the region of the electric field. So the discussion will be simple and will be simplified so that every one of you will understand these main concepts. I will assume that you have taken these concepts in the high school or probably in the 9th or 10th grade. As you see, we have two objects here. One is not charged, the one to the left is non-charged, while the one on the right, figure B, shows a positive charge. A positive charge, it occurs when we knock an electron out of the surface of this sphere using the energy that you have learned to call ionization energy. If we knock an electron from the surface, now there will be a hole, and this hole is assumed to have a positive charge. So, as you know, in figure A, there is no net electric charge, and hence no electric field. If there is no charge, no field. The C's points in random direction. In figure B, the C's line up in the direction of the electric field. Each seed experiences an electric force, and the force causes it to align with the field. The standard way to draw an electric field is shown in the figure on the next slide. So here we need first to understand what is an electric charge, because as you know, electric field is defined as the electric force per unit charge. So in order to quantify and understand the electric field, we need to understand the electric charge, and then to understand the associated electric force. The ratio between the electric force and the electric charge is called the electric field. So electric charge is a property of the particles that make up the matter. Charge can be positive or negative. Knocking an electron from the surface of a neutral sphere, for example, yields a positive charge, and adding some electrons to the surface of a neutral body will charge it with a negative charge. Charge, as you know, is measured in coulombs. Atoms are composed of negatively charged electrons and positively charged protons. We know that electrons move in orbits around the nucleus. The electrons are negatively charged, and the nucleus has a positive charge. Okay. if we take an example, look at the nucleus. It has a positive charge, the protons, and the neutrons, but the neutrons have zero charge. And as you see here, electrons are revolving around the nucleus with negative charges. Okay? Repulsion and attraction. We know that like charges repel each other. Positive with positive, they repel each other. Negative with negative, they repel each other. While opposite charges attract each other. As you see, we have a positive charge and a negative charge, and there is a force of attraction between these two charges. Space, called the permittivity of a free space, and its magnitude equals 8.85 times 10 to minus 12 coulomb squared per Newton meter squared. Let us take an example on the electric forces. 2.5 kilogram spheres are placed 25 centimeter apart. Each sphere has a charge of 100 microcoulomb. As you know, micro is equivalent to 10 to minus 6. So this charge is equivalent to 100 times 10 to minus 6 coulomb. One of them is positive and the other is negative. Calculate the electrostatic force between them. Fk Q1 Q2 over R squared. K is 9 times 10 to 9. And then if you substitute Q1 equals Q2 equals 100 microcoulomb, which is 10 to minus 6 coulomb or 10 to minus 4 coulomb. R is 25 centimeter, and you need to convert it into meter, 0.25 meter. And if you calculate the electrostatic force, you will get 9 times 10 to 9 times 10 to minus 4, 10 to minus 4 over 0.25 squared, and you will end up with 1440 Newton. Another example, as shown below, two protons are 3.6 nanometer apart. Nano means 10 to minus 9. What is the net force on an electron located on the line between them? 1.2 nanometer from one of the protons. You know, the elementary charge of the proton is 1.6 times 10 to minus 19 coulomb, and in this case you have to calculate the net force. So F net is F1 plus F2, Q1 is plus E, Q2 plus E, and we placed Q, which is an electron, at a distance 1.2 nanometer from Q1. If the total distance between Q1 and Q2 is 3.6 nanometer, then the electron is 2.4 nanometer from the second proton. So in this case, you have to find F1. F1 is K Q1 Q over R1 squared, which is K E squared over R squared. To lift. Why to lift? Because there will be an attraction between Q1 and minus Q. So it will be attracted to the proton Q1, and then the other force F2 is KQ Q2 over R2 squared, again is K times E squared over 2.4, of course, times 10 to minus 9 squared, and this will be to the right because the second proton will attract the electron to the right. And then if you plug in the numbers, you will get 0.12 nanonewton, 10 to minus 9 newton, to the left or negative x-axis, because F1 will be greater than F2, so the net force will be to the left. Now let us discuss the concept of an electric field. The electric field at point B is the force per unit charge. So E is F over Q. Unit of E is the Newton per coulomb. The electric field around a positive charge plus a Q at point B. You know, if we have a positive charge Q and at a distance r from it we have the positive test charge plus q. Then there will be a repulsive force between big Q and small q, and then if you divide this force by the charge q, you will find that the direction of the field is to the left, and the magnitude of the force is kq, big Q times small q over r squared to the left. So the electric field will be k times q over r squared. Now let us discuss quickly and briefly the properties of an electric field. If we have a charge minus q, as you see, the electric field lines will appear to be terminate on the surface of this charge, so we call always the negative charge as the sink of the electric field lines, and the direction of electric field will be radially inward. And if we take a positive charge plus a q, we see that the electric field lines are pointing radially outward. This is why we call a positive charge as a source of the electric field. So positive charge is the source of the electric field, negative charge is the sink for the electric field. The electric field lines originate at the surface of a positive charge and terminate at the surfaces of negative charge. The direction of the field lines show how a charge would move if placed in a uniform electric field. So if we have a positive charge q, and the force at it will be E over q, which means that E is, no, this is not correct. The force, now you see, we know that E is force per unit charge, so you should interchange these symbols. E equals F over Q. Okay, so if we have a negative charge, then the force will be minus Q phi E. Electric field lines between two charges. If we have a positive charge and a negative charge, then you should map the electric field lines. As you see, electric field lines originate from the positive charge and terminate on the negative charge. Okay, if we have like charges, positive and negative, now you see in the middle between the charges, you will see that there is a neutral region in which no electric field lines are crossing this region. Okay, so this is why we call this a neutral region. Again, if you have a positive charge q, as you see, electric field lines are originating from the charge, and if you place a positive test charge plus a q naught, where q naught is much smaller than big Q at point A, there is an electric force, okay, radially outward from this charge. So the electric field at point A will be Q naught times E. Q naught times E. Similarly, if we have a negative charge and we place a positive test charge Q naught at point A, this positive test charge will be attracted to the negative Q, and again the magnitude of the electric field will be F over Q naught. But the difference between figure A and B is in the direction. In the first case, the electric field lines appear as originating from a plus Q, and in part B, as you see, the electric field lines appear to terminate on the negative charge. So I explained this slide on the figure. Now let us use the definition of the magnitude of the electric field. If a small positive discharge Q naught experiences a force of magnitude F at a given location, the magnitude of the electric field E at that location is the force on the positive charge over the amount of the charge, so E will be F over Q naught. Again, the electric force then will be Q times E. So the force is the magnitude of the charge 2.8 times 10 to minus 6 times the magnitude of the electric field, which is 0.129 Newton, but in this case the direction of the electric force will be to the right, which is the same as the direction of the electric field. And in the second case, the charge will move opposite to the field, will experience an electric force in the opposite direction. So if you calculate the magnitude of the force, you multiply the magnitude of the charge times the magnitude of the electric field, and you will get 0.428 Newton. Okay, to summarize, the force on the positive 2.8 microcoulomb charge has the magnitude of 0.129 Newton and points in the positive x direction, while the force on the negative 9.3 microcoulomb charge has the magnitude of 0.428 Newton, but it points in the negative x direction. Here we have a positive charge at the origin, and we have a positive discharge Q naught. In this case, the electric force on the charge is Q naught over R squared, and then if you divide this force by Q naught, then you will get the electric field, which is KQ over R squared. This is the magnitude of the electric field due to a point charge. So if you want to find the magnitude of an electric field due to a point charge, you just multiply K by the charge itself and then divide by the square of the distance between the charge and the point at which you calculate the electric field. In this case, we see the same thing, but since the charge is negative here, so the electric field line will point towards this charge. It terminates on the surface of this charge. Let us have an example here. Find the magnitude of the electric field produced by a 1 microcoulomb point charge at a distance of 0.75 meter. So simply the field will be KQ over R squared. Q is 1 microcoulomb and R is 0.75 meter. If you plug in the numbers, you will get the magnitude of the electric field to be 1.6 times 10 to 4 Newton per coulomb. As you see here, E is inversely proportional to the square of the distance between the charge and the point at which you calculate the electric field. Electric field due to a point charge is not required in our syllabus, but just you need to have a flavor of how to calculate the magnitude of the electric field due to a point charge. What matters basically in this part is the uniform electric field. Uniform electric field. All these slides I'm not gonna discuss details. I will just skip these slides and I will go to discuss the electric field due to an infinite plate, okay, that has some charges on it. In this slide, as you see, we have a plate, a sheet of charges, and it has positive charges uniformly distributed on the surface of this plate. We will consider this plate as infinite sheet of charges. What does it mean to say infinite sheet or infinite plate? It means that the dimension of the plate is much larger than the points at which we calculate the electric field. If we have such an infinite plate and you want to find the electric field around it, as you see the electric field lines are pointing outward from the plate, the magnitude of the electric field around this plate is uniform and constant. Its magnitude will be the surface charge density sigma over 2 epsilon naught, where epsilon naught is the permittivity of a free space. Okay, then and sigma is the surface charge density. Surface charge density, you just divide the charge on the plate by the area of the plate. So E around this infinite sheet of charges will be constant, and its magnitude equals sigma over 2 epsilon naught. Sigma is the surface charge density, Q over A, and it's measured in the unit of coulomb per meter squared, and epsilon naught is the permittivity of a free space, assuming that this plate is placed in vacuum or in air. Now, what matters basically in our physics 104 is the electric field, is the uniform electric field produced between two infinite plates. Okay, why we need such a field? Because it is very similar to the electric field in the axon. It is very important to understand the electric field in our bodies. Okay, so in the nerve, we know that nerve pulses in our bodies, the neurons. Okay, in the science of neurology, as you know, we know that these nerve pulses move inside our body using uh, this what's called an axon. Okay, so we need to understand the nature of the electric field in our nerve system. Okay, this is why we should understand the magnitude and direction of a uniform electric field between two infinite sheets of charges. If you look at this slide, the electric field to the right of the negative plate or to the left of the positive plate will be zero, because if you take any point to the left or to the right, and you will see that the net electric field at that point will come from a positive plate and a negative plate. And since the two fields are equal in magnitude and opposite in direction, they cancel out. So this is why there is no field to the left of the positive plate and no field to the right of the negative plate. But if you take a point between the two plates here, you will see that there is a net electric field. The net electric field comes from the positive plate and from the negative plate, and the two fields will point in the same direction. So this is why the net electric field is obtained by summing up the electric field from the positive plate and the electric field from the negative plate. And if you sum up these two fields, you will sum sigma over 2 epsilon naught plus sigma over 2 epsilon naught, and you will find that the net electric field between the two plates is sigma over epsilon naught. Sigma is the surface charge density on each of these two plates, assuming that we have identical plates here, and epsilon naught is the permittivity of a free space between the two plates. And as you know, epsilon naught is given to you to be 8.85 times 10 to minus 12 coulomb squared per Newton meter squared. So if we have, if the dimensions of the place here are much larger than the distance or the separation between the two plates D, then we can assume that the field is approximately uniform between the two plates, pointing to the right from the positive plate towards the negative plate, and its magnitude can be calculated from sigma over epsilon naught, where sigma is the surface charge density and epsilon naught is the permittivity of free space. Okay, I think you can skip all these slides, they are not important. Okay, and and here we should also discuss the concept of electric potential energy and electric potential, because this concept is very important for the calculating the capacitance of a parallel plate capacitor later on. As you know, both electric and gravitational forces can store mechanical work in the form of potential energy. Mechanical work that is stored as electrical energy is referred to as electric potential energy. Here we have a woman, and the woman has positive and negative charge. Suppose you have a positive charge in one hand and a negative charge in the other, as is shown in the figure. Work must be done to separate unlike charges. حتى نقدر نفصل هالشحنتين، يعني in order to separate Q and minus Q, we need to apply external work. It is very similar to the work when you stretch a spring. Okay, when you stretch a spring, you have to do a work, and this work is stored as potential energy in this spring. So since the charges attract one another, you have to exert a force and do work to pull your hands apart. This work is stored in the electric field as electric potential energy. If you release the charges, they speed up as they race toward each other, converting their electrical potential energy into kinetic energy. Here, another example. If you have positive and positive charge, if you carry in your hands two positive charges, work must be done to bring like charges together, because in the natural situation they repel each other. So to bring them together, you have to do work. It is very similar that you have a spring and you compress it. So when you compress a spring, then you store potential energy in the spring. I hope this simple example will make it easier for you to understand the relationship between work done and the potential energy stored. In this example, we have a uniform electric field, and the uniform electric field is pointing downward. And then if you have a positive charge in this field, this positive charge will move with the field. It will move straight or vertically downward under the influence of a force F. This force F equals Q times E, and since the charge moves with the field, it loses energy. It loses potential energy, like you have a mass in your hand and you let it fall under the influence of the gravity. Very similar situation. So if we have a positive charge Q placed in the uniform electric field E, shown in the figure below, experiences a downward electric force of a magnitude F equals Q times E. If the charge is moved upward through a distance d, the electric force and the displacement are in opposite direction. Therefore, the work done by the electric force is negative and equal in magnitude to the force times the distance. So the work will be given as minus QE, which is the force, times Z. The negative sign comes from the 180 degrees angle between the force and the displacement. Here, let us also look at this example to point out or to figure out the close relationship between what happens to a charge moving in a uniform electric field and a mass moving under the influence of a gravitational field. From the equation, that relates work and potential energy, you should understand that work done is always equal to the negative of the change in the potential energy. We see that the systems consist of a charge and an electric field, stores a potential energy of delta B, which is equal to the negative of the work. So the stored electric potential energy is equal to Q times E times D. This is very similar to what happens when you have a ball in your hand and you let it fall under the influence of the gravity. The electric potential energy increases in this case. This is like increasing the gravitational potential energy by raising a ball against the force of the gravity as indicated. If you have a ball and you let it fall under the influence of the gravity, it will lose potential energy because its height decreases. So, but if you have a ball and you slowly raise it up against the gravitational field, so potential energy will be stored in this ball, and the change in the potential energy will be equivalent to mgd. If you compare this with this, see, for Q here we have m, for E, the electric field, here we have G, and for D we have D. So the two examples are really equivalent. The only difference between the two examples that in one case we have a charge and an electric field, in the other example we have a mass and the gravitational field. So now the unit of electric potential, as you know, is joule over coulomb. So this is called 1 volt. 1 volt is equivalent to 1 joule per coulomb. So 1 joule of energy is equal to 1 coulomb times 1 volt. Here it follows that a 1.5 volt battery does 1.5 joule of work for every coulomb of charge that flows through it. So like if we have 1 coulomb moving across 1.5 volt, then the battery will do a work of 1.5 joule. Okay. In general, the change in electric potential energy as a charge moves through an electric potential or voltage difference, delta V is given as delta P equals Q times delta V. Now we will have an example to show that. Find the change in electric potential energy as a charge of 2.20 times 10 to minus 6 coulomb moves from point A to point B, given that the change in electric potential between these points is delta V 24 volt. So delta PE is equal to Q times delta V, and if you multiply the charge by the voltage, you will get a 5.28 times 10 to minus 5 joule. Another example, in general, a high voltage system has a lot of electric potential energy. The figure below shows the situation for charges of opposite sign. When the charges are widely separated, the voltage is high. If these charges are released, a lot of electrical energy is converted into kinetic energy. So if we have a positive and a negative charge far away from each other, and if you release these two charges, they will be attracted to each other, so the potential energy stored in the system will be converted into a kinetic energy. If the two charges in the second figure are close to each other, and if you release them, then you will have a low electric potential because the separation between the positive and the negative charge is smaller than the case 1. Here, if you have positive charge very close to each other, they will repel each other very strongly. So then you will have high electric potential. A lot of energy is released when a closed space like charges fly apart. But if the similar charges are far apart at the beginning, we will have a low electric potential because less energy is released when widely spaced like charges fly apart. Again here, this figure illustrates the relationship between the change in electric potential and the change in electric potential energy. If we have a charge Q placed in an electric field E, uniform electric field E, will experience a force F. This force F is equivalent to Q times E, and if the charge moves through a distance D, then you should understand the change in the potential energy is equivalent to the change in electric potential is equal to the change in electric potential energy over the charge Q. So the change in the potential energy equals Q times delta V. Here, a numerical example to illustrate that. See, the work done by the electric field is simply the magnitude of the electric force times so the magnitude of the electric force is Q times E, and as you know, the work is Q times is F times D, and F is E times Q times D. Therefore, the change in electric potential delta V, which is delta PE over Q, should equal to minus W over Q, which is minus QED over Q, which is minus ED. This is very important relationship between the change in electric potential and the magnitude of the electric field. So connection between the electric field and the electric potential. Electric field is always equivalent to minus change in electric potential over the distance. So E is minus delta V over D, and the unit of electric field in this case is volt per meter. I here show a slide that illustrates what happens to the electric potential as a charge Q moves inside a uniform electric field from positive plate to the negative plate. As it moves in the direction of the field, it will lose energy. It will lose energy. It will lose energy. Okay? As the figure below illustrates, the electric potential decreases in the direction of the electric field. Any charge that moves in the direction of the field will lose energy. Then it is potential, electric potential decreases. Okay? In addition, the electric potential doesn't change at all in the direction perpendicular to the field. For example, now as you look here, you see that the direction of the electric field is along x-axis. If any charge moves up or down in this field, the electric potential of the charge will not vary, will not change. As the charge moves from the positive plate to the negative plate, its electric potential decreases with distance, as you see. So we have a linear relationship between electric potential and distance, and this linear relationship has a negative slope. Okay? Let us here see some examples that illustrates the relationship between electric potential energy and electric potential. So in this example, in figure A, we will see how the electric field in a capacitor can be determined, and B, how the change in electric potential energy of a charge moved between the plates of the capacitor can be calculated. So as you see here, if you look at this figure, look at this picture, we have here a positive plate, which means high voltage, and then we have a negative plate, low voltage. The electric field pointing from the high voltage to the low voltage. from the positive plate to the negative plate. See, the positive terminal of the battery is hooked up to the positive plate, and the negative terminal of the battery is hooked up to the negative plate, and the distance between the two plates is d. Okay, so let us read the example and then solve it very easily. This is very simple example that shows a charge plus a Q moves inside a uniform electric field produced between two infinite plates, one with a positive charge, which means at high voltage, and the other with a negative charge, means low voltage. In nature, the if you put a positive charge near the positive plate, it will be repelled by the positive plate and it will move down, and when it's close to the negative plate it will be attracted. So this charge will move with the field, and as you know, if a charge moves with the field, it is potential, electric potential, and electric potential energy decreases. And if the charge moves against the field, it is electric potential, and electric potential energy increases. So let us read the example and solve it very clearly. A uniform electric field is established by connecting the plates of a parallel capacitor to a 12 volt battery. If the plates have a separation of 0.75 centimeter, what is the magnitude of the electric field in the capacitor? And then and B says that a charge of a plus 6.24 times 10 to minus 6 coulomb moves from the positive plate to the negative plate. Find the change in electric potential energy for this charge. Now, as you know, delta V is minus 12. Okay, is minus 12, is given to you. The separation is 0.75 centimeter. You need to convert it into meter. So, and the charge given is plus 6.24 times 10 to minus 6 coulomb. These parameters are the known parameters, and the unknown parameters are the electric field and the change in the potential energy of this charge. So E is minus delta V over D, which is minus 12 over the distance, the separation between the two plates, and then if you divide the 12 by 0.0075, you will get 1600 volt per meter. This is the magnitude of the electric field between the two plates. And then, in order to find the change in the potential energy of this charge, it is just Q times delta V. So the magnitude of the charge is 6.24 times the potential difference minus 12, which is minus 7.5 times 10 to minus 5 joule. The negative sign indicates that the charge loses electric potential energy as it moves from the positive plate to the negative plate vertically downward. Okay, so let us have an insight in our solution. The electric potential energy of the system decreases as the positive charge moves in the direction of the electric field. This is just like a gravitational potential energy of a ball decreasing as it falls to a lower height. The positive charge will speed up as it moves toward the negative plate. It will convert the decrease in electric potential energy into an increase in the kinetic energy. So if I ask you what is the change in the potential energy of this charge, you will tell me it is minus 7.5 10 to minus 5 joule. If I ask you what is the change in the kinetic energy of the charge, because as it moves from the positive plate to the negative plate, it will accelerate, so its velocity will increase. So there is a change, there is an increase, in fact, in the kinetic energy, and you will have 7.5 times 10 to minus 5 joule. Energy conservation applies to a charged object. In an electric field, we know that the electric field is conservative, so the total mechanical energy is constant. So the change, so if a charge moves from A to B, you should understand the total mechanical energy of the charge at point E should equal the total mechanical energy of the charge at point B. So the sum of the kinetic energy and potential energy at point E should equal to the sum of the kinetic and potential energy at B. I believe you can skip all these slides because they are not يعني required from you. So I will just now talk about the capacitance and the energy stored in a capacitor. A common way for electrical system to store energy is a device known as capacitor. A capacitor consists of two conductors, identical conductors that carry equal and opposite charges and separated by an insulator, separated by a vacuum, and we assume that in this vacuum we have an insulator. We have a material that 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 is called insulator. Okay, this is the way we define, or this is the way we construct a capacitor. Capacitors are an important element in modern electric devices. No cell phone or computer could work without capacitor. يعني هذا التليفون اللي ماسكه انت بايدك is very important to understand the functioning of the capacitor in order to understand the functioning of this cell phone. Capacitance and energy stored. In general, a capacitor is nothing more than two conductors referred to as a place separated by a finite distance. The finite distance here between the two places is assumed to be filled by an insulating material. When the plates of a capacitor are connected to two terminals of a battery, they become charged. One plate acquires a positive charge plus a Q, and the other plate acquires a negative charge minus a Q. To be specific, suppose a certain battery produces a potential difference or voltage between its terminals. When this battery is connected to a capacitor, a charge of magnitude Q plus a Q appears on the positive plate, and a charge of minus a Q appears on the negative plate. The ratio of the charge stored to the applied voltage Q over V is called the capacitance, and the unit of the capacitance is coulomb over volt, and this unit is called farad. So let us summarize here. The concept of capacitance is defined as the charge on each plate over the electric potential difference. So C equals Q over V, coulomb over volt, and this is called farad. You should understand that farad is a huge unit. So in electric circuits or in devices like laptops or cell phones, you should know that the capacitor being used is of the order of microfarad, which means 10 to minus 6 farad, or nanofarad, 10 to minus 9 farad, or picofarad, 10 to minus 12 farad, or femtofarad, 10 to minus 15 farad, and so on. Uh, of course, the unit farad is after the name of Michael Faraday, and he lives between 1791 and 1867. Okay, between 1867 to 1791. In this period, he lives. Now, if I want to have a simple picture of how the capacitor stores electric charge or electric energy, we can think of the capacitor as a bucket of water. Okay, so as you see, the depth of water is the potential difference, the amount of water stored is the charge stored, and the cross-sectional area is the capacitance. So if you want to compare a capacitor of capacitance C that carries a charge Q produced by a potential difference V between the two places is like we have a storage tank or a bucket of water of a cross-sectional area C and some amount of water in it, and the depth of the water is the potential difference. This is very good picture that will make you understand the similarity between a bucket of water stores some water and a capacitor that stores electric charge or electric energy. Capacitance and energy stored. The main function of a capacitor is to store a charge or electric energy. In terms of this analogy, charging a capacitor is like powering water into a bucket. If the capacitance is large, it is like having a wide bucket. In this case, the bucket holds a lot of water when it has a given level of water. A narrow bucket on the right hand side will, with the same water level, holds much less water. This can be seen in the figure below. Let us here have a numerical example of how to calculate the capacitance and then how to calculate the energy stored. A capacitor with a large capacitance holds a lot of charge for a given applied voltage. You should know that when we say C equals Q over delta V, C neither depends on Q nor on delta V, because as V increases, Q increases, such that this ratio Q over V remains the same. It is true to say that the capacitance of a capacitor is like a fingerprint of a human person. Your fingerprint will never ever be the same as the fingerprint of another person. And this is the C. C is always defined as a Q over delta V, but C neither depend on a Q nor on delta V, because if you increase V, Q increases, such that Q over V remains the same. Later we will talk about what are the factors that determines the capacitance. Okay, in this figure we have a parallel plate capacitor that has a capacitance of 451 picofarad. 1 picofarad is 10 to minus 12 farad. The separation between the plates of the capacitor is d 0.55 millimeter, which is 10 to minus 3 meter. Find the voltage difference between the two plates of the capacitor when the charge on the plates has a magnitude of 9.06 times 10 to minus 19 coulomb, which means on the positive plate we have a plus 9.06 times 10 to minus 9 coulomb, and on the negative plate we have minus 9.06 times 10 to minus 9 coulomb. And then capacitance is always calculated from C Q over V. C is 451 picofarad, D 0.55 millimeter, and Q is 9.06 times 10 to minus 9 coulomb. This is the known quantities. The unknown is the voltage and the electric field. So the voltage will be measured from a Q over C. So it is 9.06 times 10 to minus 19 over 451 times 10 to minus 12. So the voltage across this capacitor is 20, which means that in order to charge this capacitor with a positive charge of 9.06 times 10 to minus 9 coulomb, and to charge the negative plate of a charge minus 9.06 times 10 to minus 9 coulomb, you have to apply a battery that has a voltage of a 20 volt. The electric field between the two plates is delta V over D, the magnitude of the electric field. So 20 over 0.55 times 10 to minus 3 meter. So the electric field is 36,400 volts per meter. What does this number mean? This is a huge number. It means that for every meter of separation between the plates, you should understand that the potential difference is 36,400 volts. The total amount of charge in the capacitor is plus Q and minus Q. Of course, the net charge is zero. The fact that the charge is separated with positive charge on one plate and negative charge on the other, means that work had to be done to create the separation. This work is stored in the capacitor as the electric energy. I hope you understand the idea. Now the net charge on the capacitor is zero. But when we separate plus Q and minus Q, we need to do work in order to separate the positive and the negative plate, and this work done is stored in the form of electric energy. This is the way the capacitor. The two main factors that determine the capacitance of a capacitor are plate area and the plate separation, A and D. If the area of the plate is increased, the capacitance goes up. It is just like the analogy with a bucket of water. A capacitor with a large plate area is like a bucket with a large cross-sectional area. If the plate separation is decreased, the capacitance increases. The reason is that a smaller separation between plates reduces the potential difference between them. This means that less voltage is required to store a given amount of charge, which is another way of saying that the capacitance is larger. Okay, this is a key on the keyboard. This is a button on a keyboard. A button on a keyboard is a capacitor. So look at this figure. The dependence of a capacitance on a plate separation is useful in a number of interesting applications. Each key on a computer keyboard is connected to the upper plate of a per plate capacitor as illustrated in the figure. So when you push this key, what happens? When you press on a key, the separation between the plates of the capacitor decreases. This increases the capacitance of the key. The circuit of the computer detects this change in the capacitance and determines which key has been pressed. يعني how the keyboard understands that you press on P or O or U or Y or T on the keyboard. When you press on the key, you reduce the separation between the plates of the capacitor, and this will increase the capacitance. So in the circuitry of the computer, it detects this change in the capacitance and determine which key has been pressed. As we mentioned before, capacitors store more than just a charge. They also store energy. It can be shown that the total energy stored in a capacitor is 1/2 Q times V, and since C equals Q over V, then PE is also equivalent to 1/2 CV squared, and this is also equivalent to Q squared over 2C. This is the amount of the potential energy stored in the capacitor. The energy stored in a capacitor can be put to a number of practical uses. A camera flash, for example. A camera's flash unit typically contains a capacitor with a capacitance of about 400 microfarad. When fully charged to a voltage of 300 volt, this capacitor contains roughly 15 joule of energy. Because of the rapid release of energy, this charge takes less than a millisecond. The power output of a flash unit is impressively large, about 10 to 20 kilowatt. You can really understand how the camera flash works if you understand the concept of the energy stored in a